Good morning, everyone, and welcome to this lecture. This is lecture number 4, and we are dealing with Beer-Savart law. Do we remember what we had done in the previous class? Good morning, Abhiram. In the previous class, we had seen the magnetic field due to a straight long wire. Do we remember this? Magnetic field due to a straight long wire. Do we remember the formula of magnetic field due to a straight long wire? Yes or no? Do we remember the formula of straight long wire? Yes or no? Yes. Am I audible and visible to all of you?
Yes, sir.
Do we remember the formula of straight long wire, and we had used it to find out the magnetic field due to an infinite wire? Then we had used that same formula to find out magnetic field at the center of two wires. We had used the same formula to find out magnetic field due to a wire like this. Do we remember this?
Yes, sir.
Then I gave you this question that you had to solve. This is a square of side length A, and you have to find the magnetic field at the point P. Anyone got the answer for this? Well, I'll give you I will give you 2 minutes. Try this question. This is the first question. To give you a hint, what will be the distance of this point P from any of the sides? How much will be the distance of this point P from any of the wire or any of the sides? The square is of side length A. What will be the distance of the point P from any of the sides? No one knows the distance of the center from the side of the square. No one knows the distance. No one knows it.
Sir, A by 2?
A by 2. That is correct. A by 2. And you know how much would be these angles? This angle, how much would be this angle, and this angle, how much would be this angle? Do we know this?
If it directly bisects, it will be 45. Sir, 45 degrees?
45 degrees. Now, you have all the information. You can tell me what is the magnetic field at the point P. I will give you 2 minutes to go through it. If you don't remember the formula, please go back and check the formula of a straight wire. It was mu naught I by 4 pi r into sine theta 1 plus sine theta 2. I'll give you 2 minutes to try this question and give me the answer. How did you get this answer? Okay, let us check. Let us first find out the magnetic field due to this wire. What is the magnetic field due to this wire? B will be equal to mu naught I by 4 pi. How much is the distance of this point from the wire? It is A by 2. Yes or no?
Yes, sir.
Into of sine theta 1 is 45 plus sine theta 2, that is also 45. So if I solve this, I will get what? Mu naught I by 2 root 2 pi a. Yes or no? This is the magnetic field due to Oh, sorry. It will be root 2 times, right? 1 by root 2 plus 1 by root 2 is 2 by root 2. So you will get 2 in the numerator. So this 2 will get cancelled. And I will have root 2 pi a. Yes or no?
Yes, sir.
Now we have to find out the direction. So you turn your fingers and you will see that this magnetic field will be coming outside. Yes or no?
Yes, sir.
You look at all the wires and you find out the direction of magnetic field due to all the wires. Due to all the wires, the magnetic field is coming out. Yes or no? So the net magnetic field, all the wires are same. You just multiply this answer by 4. So it will be 4 times B. If you take 4 times B, you will get 2 root 2 mu naught I by pi A, and the direction would be outside. That is the answer that we were looking at. Do we understand this? Anyone got this answer?
Yes, sir.
Good. That is the answer for this particular question. So you can save it, and then we will move on to the next type of questions. Shall we move on? Have you noted it down, everyone?
Yes, sir.
We move on to the next type of questions, and the next type of questions will be magnetic field due to a circular loop. Magnetic field due to a circular loop. So we'll just look at a circular loop. This is a complete circle and a circular loop. The radius of this loop that you will see is R. The center is C, and you have a current I which is moving in this loop, and you have to find out the magnetic field at the point C, which is the center of the loop. Remember the formula for this loop. Magnetic field at the center of the loop, my dear friends, is mu naught I by 2 R. Mu naught I by 2R. That is the magnitude. And how do you find the direction for the circular loop? Well, you can use your palm and hand, or you can do it more simply. Whenever you have a loop or wire moving in a or current moving in a loop, you just turn your fingers. You just turn your fingers in the direction of the current in the loop. Please pay attention. You turn your fingers in the direction of current in the loop. The direction of thumb will give you the direction of magnetic field. You turn your fingers. If I turn my fingers on this loop, the current is clockwise, so my thumb is going inside. That means magnetic field is inside. That is the easiest way to find out the magnetic field direction due to a current carrying loop. You turn your fingers in the direction of the loop with your right hand, and you will get the direction of magnetic field. In this case, it is going inside. If the current is clockwise, it will go inside. If the current is anti-clockwise, it will come outside. This is the formula that you will have to remember for a circular loop. Do we understand this? Mu naught I by 2R. That is the formula for magnetic field due to a current carrying loop, circular loop. Now, many a times may not have a complete loop. You may not have a complete loop. You may only have a part of the loop. If you have a part of the loop, then you do what? Don't worry. You can always devise a formula which is valid for a part loop as well. This is arc of a circle. It carries a current I. The radius of the circle is again r. It makes an angle theta at the center of the circle. The magnetic field due to this loop B will be equal to mu naught I by 4 pi r multiplied by the angle theta. Now remember this theta, this angle theta has to be in radians, not in degrees. This angle theta has to be in radians and not degrees. This will be the magnetic field due to this current carrying circular arc. How will I get the direction of magnetic field? Again, I turn my fingers. You can see this current is clockwise. I turn my fingers. My thumb is going inside. So the direction of magnetic field would be inside. This is the magnetic field due to a current carrying loop which is not complete loop, a part of the loop. In fact, if you look at formula, this formula is also derived from that formula. What I have done here, my dear friends, bacho, is that I have written it as like this. You can also write it like this: 4 pi into r multiplied by the total angle of the circle. Total angle of the circle is 2 pi. 2 pi is 360 degrees. I cannot write 360 degrees. The total angle of the circle is 2 pi. If I write it as 2 pi, theta as 2 pi, I will get the same answer. That means even if you don't remember the magnetic field due to a full loop, if you remember the formula for part of the loop, arc of the loop, you can just put the angle as 2 pi and you will get the answer for the full loop. Do we understand this?
Yes, sir.
Now, just to give you an example, if I have a semicircular loop, my dear friend, if I have a semicircular loop, now I ask you this question. If I have a semicircular loop like this, can you tell me what will be the magnetic field at the center of this loop? Can anyone tell me what will be the magnetic field at the center of this loop?
Sir,
Center of this semicircular loop, what will be the magnetic field?
mu naught I by 4r.
That is correct. You just need to put the value of angle as pi. Pi is 180 degrees. So you will get the answer B is equal to mu naught I by 4 pi r simply multiplied by pi, and that will give you the answer. Can you also tell me what is the direction of magnetic field? What is the direction of magnetic field?
Inside, sir.
It is inside. You turn your fingers in the direction and you get your answers. Have you understood this, everyone?
Yes, sir.
Everyone has noted it down. I'll give you 2 minutes to note it down. Once you are done, please let me know, beta.
Done, sir.
Then there is one more case that we should remember. In this case, the coils are not in the same plane. So the coils are not in the same plane. It is non-coplanar. But they have the same center. So we call it non-coplanar concentric coils. Non-coplanar but concentric coil, it will look like this. They will have the same center, but they are not in the same plane. I hope you understand this. You can see these two coils, yes or no? Coil number 1 is kept like this, and coil number 2 is kept like this. Do we see this, everyone? Do we see this, everyone? Coil number 1, you can call the radius as R1. And coil number 2, you can call the radius as R2. Do we understand these two coils are in different planes? Yes or no?
Yes, sir.
This is coil number 1. It lies like this in the XZ plane. And the current is moving like this. Do you see this, bacha? The current is going like this. Now turn your fingers. In which direction is the magnetic field going because of this pink coil? Tell me. In which direction is this field going? It will be going in the upward direction. Yes or no? No, yes.
Yes, sir.
We get this, yes or no? Pink coil, upwards. We get this. Then we have this green coil, which carries current like this. So you turn your fingers like this. And you can see the magnetic field because of this green coil is going in the rightward direction. Do we see this? B1 and this B2. They are going in different directions. So just remember the value of B1 is mu naught I1 by 2 R1. The value of B2 is mu naught I2 by 2R2. These two are perpendicular to each other. Are you paying attention, beta? Are we there, everyone?
Yes, sir.
The net magnetic field in this case will be under root of B1 square plus B2 square. So please note it down. Two rings, two coils, but not in the same plane. I will give you 1 minute to note this down. Okay, so these are the cases for the coil. There is okay, we'll do that case later on. Let us move ahead and solve some problem based on this circular loops, and then I'll get back to this. which is the first problem that we are going to do. So this is the problem that I am going to give you first of all, and I hope that you give me the answer quickly. Same question can come in your NEET beta, so please be careful. This is the question that is coming on your screens. Question number 1. Find the magnetic field at the center O of the arrangement that is shown here. This pink wire is coming from infinity and it is again going to infinity. We understand this, yes or no? And you have to find the magnetic field at the point O. The 4 options are given to you, bacha. So I'll give you 2 minutes to give me the answer for this one. So quickly, answer option C. That is correct. Option C is the correct answer. It is exactly correct. Option C. As you can see, this wire will not create any field because the point lies ahead. This wire will not create any field because the point lies behind. The only wire, my dear friends, which is going to create any field will be the semicircular wire. We have already seen the field of the semicircular wire. The field of the semicircular wire is mu naught I by 4r. You just turn your fingers, doing, and you get the answer for this one. Everyone understands this? Can I have raised hands from everyone, boys, girls? You understand this question? Yes or no?
Yes, sir.
Okay, since you have done this question so quickly, that has prompted me to present the next question, and I will not waste any more space. I will just put this question here in the space that I have. And here comes the next question, question number 2 on the same screen. This is the question. The current is not given. You can take the current as I, not a problem. Can I have the answer for this question? I'll give you 2 minutes to give me the answer. And the correct option is yes.
C.
Option B is the correct option. As you can see, my dear friends, this and this wire is not going to create any field. The field will only be created by this wire. It will be inside, and
Sir,
the lower wire, which will also be inside. You can see the current is moving in the same direction. So both the magnetic fields are in the same direction, which is inward. So both the magnetic fields mu naught I by 4 R1 plus mu naught I by 4 R2, they are going to get added. You can see the current is in the clockwise sense. The current is in the clockwise sense. Whether you look at the upper part, the blue part, the current is in the clockwise sense. You look in the green part, the current is also in the clockwise sense. Both are going to get added up, and therefore I have the answer. Do we understand this? Yes or no? No, yes. We understand the answer, beta. We got this? Yes or no? Got it,
Yes,
sir.
sir.
Then I put forward the third question in this category. There were 3 questions there. This is the third one in the category coming on your screen, same screen right now, so that you can understand the difference between the 3 questions. This is the third one in the same category. I'll give you 1 minute to think about it and get me the answer. What is the answer in this case? Again, this wire and this wire is not going to do anything, so don't worry about them. The green wire. In which direction will the green wire create field? Inward or outward? The green wire will create field in the inward direction. Yes or no? It's clockwise current. The blue wire will create current will create field in what direction? Remember, it is anti-clockwise. So it will create
Outward.
outward. Which one will be stronger? Inward or outward? Which field is stronger? Inward field or outward field? Current is same. The inward field is stronger. Yes or no? I told you inward field is stronger because it is inversely proportional to R. Inward field is stronger. So the
Sir,
answer
option C.
would be option A, mu naught I by 4, inward minus outward, and the direction is inward. That is how we get this. Do we understand this?
Yes, sir.
It was so simple, sir. I hope you got the answer, sir. Yes or no, sir? You understand this, sir?
Yes, sir.
Comes the next set of questions, sir. And I hope you don't disappoint me, sir. This question, sir. Current in the circuit is I, sir. And I'll give you 2 minutes, sir, to give me the answer, sir. Actually, I'll give you two questions. Let me give you this question as well, and I'll give you 2 minutes so that you can think about both the questions. I hope you see both the questions. Yes or no? No, yes. And I'll wait for your answers for both of these questions. Yes, do I have the answer for the first question? First question. This angle is given as 90 degrees. So how much is this angle? This angle will be 270 degrees. Yes or no? Yes or no? 270 degrees in radians is 3 times of pi by 2. Pi by 2 is 90. 3 times pi by 2 is 270. So we just apply the formula. B will be equal to mu naught I by 4 pi r multiplied by 3 pi by 2. Pi and pi getting cancelled. So your answer will be 3 mu naught I by 4r. You just have to see the direction of current to find out the direction of magnetic field. The current is moving in the anti-clockwise sense here. So the direction of field is pointing towards me, and therefore the correct option is option D. Anyone got this answer?
Yes, sir.
Well done then. You have done one part correctly. Now we come to the next question. Next question, I have three wires. Let us first talk about the pink wire. The pink wire is going like this. What type of wire it is? It is a semi-infinite wire. Yes or no? The magnetic field due to this semi wire, let me call it as B1. It will be mu naught I by 2 pi r. Do we remember the formula? Yes or no?
Yes, sir.
And the direction of field will be, current is going like this. Point P is downward. So if I turn my fingers, it will be coming in the outward direction. Yes or no?
Yes, sir.
Well done. Then I have this blue wire. This blue wire is a semicircular wire. So I can write the magnetic field due to this semicircular wire. Let me call this as B2. B2. It will be mu naught I by 4r. Yes or no?
Yes, sir.
And if I turn my fingers, it will also be going in the outward direction. Yes or no?
Yes, sir.
What is left is the only wire, other wire, which is the green wire, which is again a semi-infinite wire, bacha. B3 I will call it mu naught I by 2 pi r. The field is same as the pink wire. Let us see whether the direction is what. Current is here, point P is upward.
Outwards.
Outward. That means all the field are outward. Everything is getting added up. There is only one option which is correct. And which is that option? Option B. Do we understand this? Yes or no?
Yes, sir.
Everyone understands this?
Understood, sir.
Then I give you this one.
1 minute, sir.
Okay.
Completed, sir.
Completed, sir. Well done, sir. Let me see if I have more for you, sir. I think we are done, sir. I think we are done. Okay. What we got to do now, bacha, is to note down some important results where the magnetic field is going to be zero. I have seen straight questions coming from this, and I've compiled this list from your previous year papers and what can come and what cannot come. So please note these results very, 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 very carefully. And these are the revolutionary results coming on your screen now. In all these cases, what you see is current coming from one side. It's getting divided. Some place it is getting divided in a circle. In some place it is getting divided in a square or a rectangle or a triangle or a cuboid or a cube. In all these cases, what is going to happen, bacha? The blue wire and the green wire have current in opposite direction. So what they are going to do, bacha, they are going to cancel each other's field out. They are going to cancel each other's field out. And in all these cases, on all these cases, the magnetic field at the center point is zero, because all these wires, whichever wire I call blue and whichever wire I call green, they are going to cancel each other out. Do we understand this? So in all these cases, my dear friends, the magnetic field is going to be zero, zero, and zero, and zero. Magnetic field is going to be zero. I'll give you 2 minutes to note this down. Everyone has noted this down, yes or no?
Yes, sir.
Well, then that will be the last thing for today's class. We are almost done with Biot-Savart law. The next class we'll move on to one more small thing that is there. That is the Ampere's law. And then we will wind up this chapter, this part of the chapter in the next class. Two things are remaining: magnetic field due to a loop on the axis point. I will give you the formula for that, and I'll also give you 2 or 3 examples on that, so that we will do it, because it cannot be done. 2 minutes left, cannot be done in today's class. So we will continue this in the next class, and I'll see you tomorrow. I hope all of us have understood to find out the direction of magnetic field and the values. One of these questions is going to come in your exam. If it comes from this particular topic, it will be from this question that we have already done. And remember all the zero magnetic field cases, one of these question may come. So I'll see you in the next class. Take care. Have a good day. God bless all of you. Bye bye.
Bye, sir. Take care, sir.